Hi folks, welcome back to Bennett's Chemistry 12 tutorials. We're moving on to a kind of a different method of balancing a redox equation. So in the last episode, in episode 27, I showed how to go about doing balancing a redox reaction using the half-cell method, which has its pros and its cons. And as promised, I'm going to show you how to do the same type of thing, just using a different technique. So using oxidation numbers rather than a half-cell technique. And this method also has its pros and its cons. Once you learn how to do it, and you kind of get an understanding for what a redox reaction is and the two halves of the redox reaction, the reduction and the oxidation, and you understand that there's a transfer of electrons, and the transfer of electrons has to be equal between the oxidation and the reduction. Using your oxidation numbers technique will be a little bit faster, okay? Especially if you get good at it, you tend to go pretty quick at it. And so once you learn this technique, you might say, forget the half-cell method. I'm going to stick with this method. And that may very well be the case. Both of them work. There's certain benefits to each one of them. Okay, so as I did in the last class, I wrote down the steps of how you're going to go about doing this technique. So using the oxidation number technique, obviously, the first step is going to involve assigning oxidation numbers. And so the steps are right there for you. Okay, so take a snapshot of that and then have that, or write it down, or do whatever. And then again, just like in the half-cell method, once you've got the steps in your mind, you kind of go, okay, done, 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 done. And when you get to the very last one here, you're balanced. Like once you actually get down to step number 6 there, once you've done that last step, you've got a balanced redox reaction. You move on. Okay, so the one that I've got up here on the board, carbon monoxide and tetraatomic phosphorus forming phosphate and methane. Okay, so first thing, I wrote this up here and I kind of put it up above because I didn't have room. So it means in an acidic environment. So this might be happening with acidic solution around, okay, or this happening within an acidic solution. So you might have a chunk of P4 sitting down at the bottom of a solution that has carbon monoxide dissolved in it. Okay, so not the most likely of scenarios, but that's kind of the scenario that I've got up here for you. Okay, so first thing we need to do is we need to assign oxidation numbers. That's step number 1. So I go through every atom, and they're separate. Like I don't have to worry about the carbon over here and the carbon over there compared, not right now. I just need to know what's the oxidation number of everything. So to go through how do you get the oxidation numbers of something, go back to the first episode of the Redox series, which I think was episode 26. Go to the second half or so of that, and I go through the whole explanation of oxidation numbers, what they mean, how you assign them, the priority list, and things of that nature. So I'm not going to spend a lot of time going over why the oxidation number is what it is. I'm just going to go through the process. I'll say it out loud, what's going on in my head, but I'm not going to slow down and explain anything. Okay, so the first one, carbon monoxide, oxygen has higher priority, so I'm going to put a little -2. I'll put it in red. I'm not sure if it's super big there, but hopefully it's big enough you can see it. -2. That means the carbon has to be +2 for it to come out to neutral. P4, doesn't matter that there's 4 of them, that's elemental, so that phosphorus is 0. Over here on the other side, the oxygen again is -2. -2 times 4 is -8, has to come out to a -3. That means the phosphorus is +5 in the phosphate. And then over here, hydrogen has priority. Hydrogen is a +1. That means +4 from the hydrogens. The carbon must be -4. Okay, so this technique kind of relies on can you do oxidation numbers? Like, are you efficient? You don't make mistakes? Can you do the math in your head? Do you not mess up whenever you make or assign oxidation numbers? And you have to be able to do it fairly quickly, otherwise you kind of lose the advantage of doing this technique. Okay, so that's the first thing. If you notice the half cell method, you don't need to know about oxidation numbers or how to get them or anything like that. There's a technique there that doesn't rely on oxidation numbers. This one obviously does. So you got to know your oxidation numbers, and you have to be able to do them pretty quickly as well. Okay, so that's our first step, is to assign oxidation numbers. Our second step is to identify the reduction and the oxidation half cells. So you need to kind of look at what you've now written down as oxidation numbers, and you need to be able to identify and actually usually draw a line actually connecting the two. So just quickly look at the oxygen, -2, -2. So the oxygen didn't do anything. All the oxygen atoms are in the same oxidative state. Therefore, the oxygen wasn't actually part of the redox reaction. That means the carbon and the phosphorus must have been what was doing the actual reaction. So the carbon went from +2 to -4. So +2 to -4 is a reduction. So you actually write down reduction and then, because it went from +2 to -4, that means that it must have added 6 electrons per carbon atom. Okay, so again, per carbon atom. So there's what the carbon was doing. The phosphorus, and might get a little messy here, but the phosphorus, and remember we're talking about each phosphorus atom. We're not talking like all 4 of them are doing the total number of electrons. It's per phosphorus atom. I've got 0 to +5. So that's an oxidation. Of 5. Okay, so the reduction here is 6 electrons. The oxidation is 5 electrons per atom. Okay, critical that you understand that it's per atom. Okay, that's step number 2. So what I've done is I've identified the reduction and the oxidation. I've written down which one is which, and I've also indicated how many electrons are either being produced by the oxidation or gained by the reduction per atom. Step number 3, balance the non-oxygen, non-hydrogens. Okay, so, and this is kind of a critical one, but you'll notice that after I said balance the non-oxygen, non-hydrogens, I said be sure to multiply the electrons by that factor as well. So whatever you're doing there. So what I mean by that is, let's look at the carbons. There's 1 carbon on this side, there's 1 carbon on this side. So they're 1-to-1, they're already balanced. Okay, I don't need to touch that one. But the phosphorus, there's a 4 there and there's a 1 there, which means that you have to put a 4 in front of the phosphate. Now when you put the 4 in front of the phosphate, that means that the oxidation up here, the 5 electrons, was per phosphorus atom, but that's happening 4 times, right? Because there's 4 atoms. So it's actually times 4 equals 20 electrons. So it's kind of critical that you take the per atom idea, but then once you balance the atoms that are actually going about doing the oxidation or the reduction, that you actually multiply the electrons, because now you say for the P4s turning into the 4 phosphates, there's a total of 20 electrons being produced by that oxidative process, okay? So now the reduction is 6 electrons. Now the oxidation, the total phosphorus oxidation, is 20 electrons. Okay, so that's step 3. Step 4. Multiply each half reaction in order to get the electrons balanced. Okay, so the lowest common multiple. So you look at your 6 and your 20 now, and you say, okay, so what's the lowest common multiple of 6 and 20? And you might say, well, just multiply them together and it's 120. Or multiply this guy by 6 and this guy by 20. You're not going to have the lowest coefficients then, right? So you'll have to reduce at the end of all of this. So it's easier to just stop and think for a second, what's the lowest common multiple? So the lowest common multiple is 60. So 20 goes into 60 3 times, and obviously 6 goes into 60 10 times. So what I'm going to do is I'm going to take this guy and I'm going to multiply by 3. And how does that look? It means that I'm putting a 3 there. I'm multiplying the phosphorus, the P4, by 3. And I'm multiplying this guy by 3. But there's already a 4 there. So I'm going to take that 4, go times 3. I'm going to erase it. And that becomes a 12. Okay, so that 3 times 20 is 60 electrons are transferred out of that oxidation half cell when 3 of those form 12 phosphates. That's what I'm essentially saying. Taking this guy and multiplying by 10. So what does that look like? It looks like I put a 10 in front of here and a 10 in front of there. Okay? Now, once you're kind of at this stage, what you've essentially done is you've taken care of all the electrons. The electrons are balanced. Okay, so I've had 60 electrons transferred from the oxidation to the reduction, and that's what I've shown so far. So essentially what I can do, if you want, is you can erase everything at this point, other than what you've put in as coefficients. So really, I can now get rid of that. I can get rid of this. And I can get rid of the oxidation numbers. Now remember, it was in an acidic solution. So now, like I've used the oxidation numbers to figure out what's reducing, what's oxidizing, how many electrons were being used. I've used that to figure out what's the total number of electrons being transferred between the oxidation and the reduction. So now I'm at that stage. Really what I have to do now is I have to balance the oxygens and the hydrogens. And so the last 2 steps are balancing the oxygens and the hydrogens. That's all it comes down to. And you'll see that when you do this, the charge will also match up. Okay? So, next thing I do is I balance the oxygens by adding waters. So you just got to make sure that you don't miss anything here, right? So I've got 10 times 1, so I've got 10 oxygens over here. So I've got 10 oxygens. You don't have to write this down. I'm just doing it to kind of demonstrate what I'm saying. 12 times 4 is 48 oxygens over here. Okay, so there's a difference of 38 oxygens. Right? So how do I get 38 oxygens? Well, 38 water molecules, because every water has 1 oxygen to it. So this side is short oxygen, so I need the water over here. And I've kind of run out of room. So I'm going to put it just up here. 38 H2Os. And if I put 38 H2Os up there, 38 plus 10 is 48, and we're balanced. Okay. So I've got 38 waters over on that left-hand side. So now the last step, according to step number 6, says balance your hydrogens using H pluses. Okay, so I have 38 times 2. So I have 76 hydrogens over here. I have 10 times 4, I have 40 hydrogens over here. So 76 and 40 have got a difference of 36. They need to go on this side. So plus 36 H plus. Now, I should be balanced. Like everything should be balanced at this point. So I might quickly go through and just make sure that everything's balanced. So let's go through every single atom. So 38 times 2 is 76 hydrogens. 10 times 4 is 40, plus 36 is 76 hydrogens. Tick. 38 times 1, 38. 10 times 1 is 10. 48 oxygens on the left-hand side. 12 times 4, 48 oxygens. Tick. Carbons, 10 times 1 is 10. 10 times 1 is 10. Carbons, tick. Phosphorus, 3 times 4 is 12. 12 times 1 is 12. Phosphorus, tick. So all the atoms are conserved. Like they're there. So now one of the really critical, tricky ones is the charge. Okay, so let's do the charge. Neutral, neutral, neutral. Oh, the left-hand side's neutral. Cool. The right-hand side, 12 times negative 3 is negative 36. 36 times plus 1 is positive 36. Negative 36, positive 36 comes out neutral. Excellent. So this must be my balanced redox reaction in acidic solution. If it was basic solution, I would then add 36 hydroxides to that side and this side. 36 waters would form over there. It would cancel this, and you would end up with 2 waters on the left-hand side plus 36 hydroxides on the left-hand side. And these H pluses would then disappear. Okay? So you convert to a basic solution from the H plus. If that was a little fast and you're like, what was that all about? Right at the very end of the last episode, I went into a little bit more detail of how you convert from an acidic to a basic solution. The other one little thing that you might notice or you might rate is that these guys right here and these guys right here happen to form phosphoric acid. So 36 H pluses and 12 PO4 minus 3s, you could write it in a slightly different form. You could put them together and you could say that and that makes 12 H3PO4. Which is a very likely form of how it will actually be written on a piece of paper or in stoichiometry, because that's the formula equation for phosphoric acid. Okay? And then you have 38 water plus 10 carbon monoxides plus 3 phosphoruses. And there's your balanced redox equation. Now, that was even slower than it probably would be, because you'd go, once you have these steps, you kind of go tic-tac-toe, and you'd have everything done really, really quickly, and bang, there, your answer would just be there. Okay, and once you do that last step of adding the hydrogens, your answer's there. You move on, kind of thing. Okay, so that is balancing using oxidation numbers. It obviously, the kind of the linchpin of the entire mass is you have to be able to do an oxidation number and not make a mistake. If you mess up just by one little thing, like if you said it was -2 and it was actually -3, well then the number of electrons is wrong, what you multiply is wrong, and everything goes haywire if you can't do an oxidation number. So that's kind of critical, right? So that's why this technique may not be for you if you happen to struggle a little bit with doing the oxidation numbers. Okay, so next class, we're moving into the electromotive force. So the voltages that, or the potential energy that these electrons have to go from one chemical to the other. And that is measured in physics. If you remember your physics classes, it's measured in volts. Okay, and so because there is a potential of an electron to move from one atom to another, you get a voltage from that. And that voltage that you get tells you something about the spontaneity of the reaction. If the electrons have the potential to actually move, it'll be a spontaneous reaction. If they don't have the potential to move, they want to stay where they are, then that will be a non-spontaneous reaction. So we'll get into all of that. We'll learn about a new chart, the standard reduction potentials chart, which if you're going to watch the next video, you should probably bring that little chart along. I will have mine, but you'll have a hard time seeing it on the screen, so it's really nice to have one right in front of you. They're all over the place. You can get them online. You probably have one from your data booklet from your own class. It's in your textbook. I mean, it's everywhere. Different versions, of course, are going to be out there, but the numbers are going to be the same. So I'll be getting into that next class. And then once you've done that part of it, then you can actually move into a little bit more of the electrochemistry part of it all. Okay, so we'll see you next time, and we'll go over E-naughts, or electrical potentials, and spontaneity of redox reactions. Okay, and we'll see you then.